Hello everyone. So I welcome you to the live section of the quantum mechanics course. I am Gitanjali Jana. So I am a PhD student of IIT Delhi. In this live section, I will solve some of the problems which will help you to understand the concept of quantum mechanics better. And if during this section, if you have any doubts, then you can stop me anytime. You can ask me the questions, as well as if you have any question while solving the problems also, then please free to ask me. Please free to stop me anytime and ask me the doubts. So uh, any so only two of them are here. So let me start the section. So before solving the section, so uh, let me tell you some of the postulates and some of the concept that can be used to solve the problems which I am going to solve today. So let's get started. So so first I will talk about some of the my voice is audible, right? Okay. Let's see some of the basic postulates of quantum mechanics. So the first postulate, it talk about the state of any physical system. Like in classical system, we represent the state of the particle by position or by momentum. If we know the position and momentum of the particle, then we can easily find out what is the state of the particle in any other time. So similarly, in quantum mechanics, what we do, we represent the state of the particle by a gate vector, which is given here. So in quantum mechanics, what we do, we represent the state vector by psi of t, which is nothing but a gate vector in the Hilbert space. So so in quantum mechanics, what we do, we represent the state of the particle by this gate vector, and this gate vector can be used to know what is the state of the particle at any other time, or to find out what is the energy of the system, or if you want to find out what is the angular moment of the particle, then you can use this psi of t to find out the state of the system. So this is postulate one, which talk about the state of the particle. So now coming to the second postulate, the second postulate talk about what is the measurement of the system. Like in classical system, what we do, we measure the position of the particle, we measure the momentum of the particle, linear momentum, angular momentum, energy. Similarly, in quantum mechanics also, we measure the to measure the any measurable quantity. What we do, we represent this observable by an operator a. Like let's say we have an operator, let's say position. So position in classical mechanics we represent by r. So what in quantum mechanics, what we do, uh, in quantum mechanics, we represent this observable by an operator, which is R, R cap. So, in quantum mechanics, we represent any kind of observable by an operator A. So, for any, if you want to measure any kind of observable, or any kind of, if you want to measure the energy, let's say if you want to measure the energy of the system, then what we do is you take the Hamiltonian operator. So, by taking the Hamiltonian operator, and by acting this Hamiltonian operator on the state, let's say psi of t, then you can easily find out what is the energy of the system, what is the energy that will get you will get after the measurement. So this is all on. So this is about the operator that you use to measure any kind of uh, measurement. So let's see the third postulate. The third postulate is it talk about the action of an operator A on a state psi of t. So this operator A, it can be any kind of operator. It may be a position operator, it may be a angular momentum operator, or it can be a Hamiltonian operator. So, uh, so, so how can we represent this action of this operator on a psi of t? Let's say we have initial state psi of t. This is the initial state that you have before. So if you now act the operator A on t, then what will happen is the state of the particle will change. So now here in this equation you can see the A is acting on the initial state psi of t, and the state now get changed to psi dash xt. So generally this psi dash xt is different from psi of xt. It's not similar to psi of xt. So the only case this A of psi of t, this psi of t must will be equal to this psi dash xt. This will be equal to psi of xt only when if the psi of xt is an eigen vector of the operator A. So you know that if the A is a psi of xt is a eigenvector of A, then you can easily write A psi of xt equal to some eigenvalue A and psi of t. Okay. So the next thing is about the what you will get after acting this operator A on the state psi. So generally, if you act a operator A on a state psi of t, what you will get is the eigenvalue of the operator A. So the result will be the eigenvalue of operator A. So if let's say the operator A is eigenvalue is an, so after acting this A on psi of xt, then you will get one of the eigenvalue of operator A. So the next thing is if you let's say if you are acting the operators A on a state psi of t, then you know that you will get one of the eigenvalue an of the operator A. Then then what is the state? It is the result you will get, but what will happen to this state psi of t? So psi of t will be changed to one of the eigenvalue of the operator A. Okay, so if an is the eigenvalue you are getting after the measurement, then what you will get is the psi of t will now become the eigenvalue, let's say phi n, which correspond to the eigenvalue an. So now if you write it properly in this equation, I have written what will happen when a arbitrary operator acts on a state. So if A acts on a state psi of t, then it will get changed to an and psi of n. Here psi of n is the eigenvalue which corresponds to this eigen. This is the eigenstate which correspond to the eigenvalue an. So an you can write it as a inner product of psi n with yn, psi n with psi of t. So now this is all about what will happen to an initial gate if you act any arbitrary operator on a state psi of t. So now the postulate 4. Let's see the postulate 4. The postulate 4, what it's talk about is talk about the probabilistic outcome of the uh, measurement. So if I told you in the postulate 3, if you act an arbitrary operator A, then the result you will get is the eigenvalue of the operator A. So it's not like you will get 100% of the eigenvalue, like you will get a different result. So what kind of how much percentage of result you will get, then for that what we do is we take the probabilistic outcome. Like let's say if an is the if is the eigenvalue of a, then to find out what is the probability of this operator, probability of getting the eigenvalue an. So the probability is getting it is written by this equation, that is an square divided by psi. So this an is nothing but the inner product of psi n with psi. Okay, this is about the what is the probability that you will get, the probability that you will get a value n in the system. So here this formula is applicable to a system when n is non-degenerate eigenvalue. Like non-degenerate means if let's say you have an and am eigenvalue. So we say an is non-degenerate when it is only when only it has only one eigenvector. So only one eigenvector is there for this eigenvalue an. But if this eigenvector an, if it has more than one eigenvector, then in that case what we say is an is a degenerate eigenstate. Okay, so let's say n is m degenerate, m is any integer number. Then for that, what we do, the probabilistic outcome is given by this equation. So this is the first equation is only for degenerate eigenvalue. So non-degenerate eigenvalue. So if you have a non-degenerate eigenvalue, then you should use this equation. But if the eigenvalue is degenerate, then what you have to do is you have to just take the inner product of all this eigenstate with the initial gate psi. Here psi is the initial gate and psi of nj is the or the eigengates corresponding to this eigenvalue an. So this you can simply write as an j square divided by psi. So now if in this equation, if you are finding that psi of inner product of psi equal to 1, then what we say is psi is normalized. For that case, what will happen to the probabilistic outcome is the p and n is given by only an square for the non-degenerate case, and for the degenerate case we will get this probabilistic outcome. So these are the way in quantum mechanics that in which you can find out what is the probability of a measurement. So coming to the last postulate, the postulate 5, it tells about what is the time evolution of an operator psi of t. So if you have any state psi, then it's not like it will not change over time. So it will change. So some of the state will change, it will evolve, and it will change. It will change to any other ket psi. So to find out what will happen to the initial gate psi of t, what we use is we use the time dependent Schrodinger equation, which is given by this form. So this I think all you know. This is the time dependent Schrodinger equation. So this is given by IH cot dou by dou t psi of t equal to h psi of t. So by solving this equation, you can easily find out what is the expression for the wave function after any time t. Okay. So These are all the postulates of quantum mechanics that you can use to find out the, let's say, the result of any kind of measurement. What is the probability of getting that measurement? So for all that, you can use these postulates. So, okay, these are some of the observable and its quantum mechanics representation. Like if in classical mechanics, we represent the position operator by R, and we represent the linear momentum operator by P, and we represent the angular momentum by L, and the kinetic energy is given by T. So in quantum mechanics, we represent this observable by operator R. So for position, it is R cap. For momentum, it is minus IH cot del. So from that, you can easily find out what is Px. Px equal to minus IH cot dou by dou x. This I think you all know the momentum operator representation in quantum mechanics. So Py is minus IH cot dou by dou y. Similarly, Pz equal to minus IH cot dou by dou z. So this is about the linear momentum. So for the angular momentum, so in classical mechanics, what we do, we represent angular momentum as cross product of R cross P. So now if we convert into this quantum mechanics, what we do is we simply replace this observable by operator. So this is nothing but R cross P cap. So P cap, you know, minus IH cot del. So just put minus IH cot del, then you will get the expression for the angular momentum is given by minus IH cot R cross del. Similarly, for the kinetic energy, you know, it is represented by P square by 2m. So if you now convert it to the quantum mechanics part, then you will just put minus IH cot del for the P. So you will get this one minus h cot square del square by 2m. Okay, so if you want to find out the quantum mechanics representation of any kind of arbitrary operator, what you have to do is you just have to replace the observable by operator. So if the observable have momentum p, then you can simply replace it by minus IH cot del. If it is let's say R, then you can represent it by capital R cap. So in similar way, you can find out what is the quantum mechanics representation of a classical observable. So this is all about the postulates. Though, so the last thing I want to talk about is the commutating operator and non-commutating operator. So this I have told before, but now I will talk about what is the why we need to study about this commutating operator and non-commutating operator. Like why do we care whether these operators are commutating or non-commutating? So it turns out that this is the definition of a commutator operator. Like if you have two operators, let's say A and B, so the commutator of this operator is given by this equation: AB equal to AB minus BA. So if AB commutator equal to 0, what we say is AB are compatible to each other. And if AB are not equal to 0, then AB are non-compatible to each other. So let's see what do we mean by compatibility. So if AB equal to 0, then we say that AB are compatible operator. So that means if we measure A and B, then and let's say we first measure A, then we measure B, which is represented by, let's say we have, let me give you an example. Let's say the state of this system is psi of t. Now you measure B operator on psi of t. So the resultant state will be B psi of t. Now we measure A. So what is the resultant state? The resultant state will be A B psi of t. Now what we do is we reverse the order. Like instead of first measuring the B, we what we do, we measure A first. So the state will become A psi of t. Now if we measure the operator B, then it will become B A cap psi of t. Now if you see, let's say this is some psi days and this is some psi, let's say it is psi 1, it is psi 2. So if you have AB equal to 0, then that means AB minus B equal to 0. So that means AB equal to BA. So that means AB equal to BA. So this means that the ordering doesn't matter. Like in any kind of order you take, you will get the same result. Like so here psi 1 equal to psi 1 equal to psi 2. So these states are same. If they are commutating, then you will get the same state. Now if here I've written if they are commutating, let's say a b equal to psi of t, then you will get this resultant state phi n. A and bn are the eigenvalue of a and b. So similarly, if you operate B, then A, then you will get A and B, and same result you will get if they are if they commute with each other. So for this compatible operator, what we have also is that we can express the AB operator in terms of a common eigenstate. So let's say we have a state, let's say we have a state phi n, which is the eigenstate of B. So if AB are commutating, then you can also write A operator in terms of this eigenstate of B. So they both share the common eigenstate. Okay. These are the properties of a commutating operator. So, as I said, the order in which they act on a state, it doesn't matter. So, any kind of order, they will give the same result. Now, in contrast to this, if you have AB equal to not equal to 0, so that means they are incompatible. So, in this case, now the ordering will matter. So now if you, let's say if you measure A first, then measure B, then in the second case, you measure B first, then A, then for both the cases, the results will be different. So AB psi of t will not be equal to BA psi of t. So for this case, you will get different result and you will see that the results will be different. So this you have to uh, you have to cautious about you have to see whether if you have a system where two kinds of operator are acting with each other, then you have to check whether they are compatible or not. If they are not compatible, then you will get different result. If they are compatible, then you will get same result. Like let me give you another example. Like you know that the position operator and the momentum operator, you will get IH curve here. So this means the commutator of position of operator with like x position of position of operator x and the x component of the momentum operator, it's they are not equal to 0. So for this case, if you act on this operator sequentially, then you will get different kinds of results. Okay. So similarly, this is for the x component. Similarly, for y component, for z component, you will see same kind of result. But if I take y cap and px, then this is 0. They are compatible to each other. Like the y component of the position and the x component of the linear momentum, they are compatible. So in this case, in any order you measure the system, you will get same kind of result. So only for the x component of a position operator and its corresponding x component of linear momentum, it is non-zero. Okay. So similarly for y, z. So this is okay. This is all about the postulates and the some of the important physical significance of compatible and incompatible operator. So I hope you all have understand what I've said about the postulates. So let us see some of the problems that these problems are related to the postulates, and these are uh, quite lengthy, but this will help you understand the postulates better. So, uh, while solving the problems, if you have any doubts, so please stop me there only so that I can clarify your doubts there only. Okay, so let me read out the first problem for you. Uh, it is given, consider a consider a system whose state is given in terms of orthonormal state of three vectors phi 1, phi 2, phi 3 as this. So what is given to you? So given to you is the state of the system, which is root over 3 phi 1, 2 by 3 phi 2, and another one is root over of 2 by 3 phi 3. And it is given that this state phi 1, phi 2, phi 2, phi 2, phi 3, they are orthonormal. So up to, I think till now everyone know about what is orthonormality. So let me just write it down for you. So orthonormality is nothing but the inner product of phi y with phi j, which gives Kronecker delta, and it is 1 when I equal to j and 0 when I not equal to j. Okay, so now this state is given to you. Now it is telling about verify that psi is normalized. So psi is normalized. I think everyone now can check. You just have to find out whether psi is equal to 1 or not. So this is the orthonormality condition. So psi is given. So let's find out what is the bra of this psi, which is nothing but the dagger of the kate vector psi. So this will become root over 3 by 3. The kate vector will become bra vector. And these are constant 2 by 3 root over 3 by 3. So they won't change. And the last one is root over of 2 by 3 phi 3. So what you have to do is take the inner product of this bra vector with the kate vector. So this will now become 3 by 9 phi 1 phi 1 plus 4 by 9 phi 2 phi 2 and 2 by 9 phi 3 phi 3. So I have neglected the other terms like phi 1 with phi 2, phi 1 with phi 3 because they are 0. So don't include this term. Only this term are non-zero. And as these states are orthogonal, then these states are 1. The inner product will be 1. So now if you check, then it is 1. So that means it is size normalized. Now let's see the next question. It is verify that size normalized. So we have checked the size normalized. Then calculate the probability of finding the system in any one of the state phi 1, phi 2, phi 3 and phi 3. Phi 1, phi 2 and phi 3. So now it is asking about the probability. So here you can see the state is given as a linear combination of phi 1, phi 2, phi 3. So now it is asking about what is the probability that after a measurement you will get phi 1 or phi 2 or phi 3. So how can you check then? So for that what you have to do. So probability is nothing but is the postulate tells the probability of getting a state, probability of getting a state, let's say getting a state phi n is given by p phi n, which is equal to phi n and inner product of this state which you want to find out, and the initial state psi square divided by psi psi. This is how you calculate the probability. Now you know that this is 1. So the probability is nothing but probability of getting a state is simply phi n psi square. So let's see what is the probability of getting state phi 1, probability of getting state phi 2, and probability of getting state phi 3. So P of phi 1 is nothing but the inner product of phi 1 with the initial kth vector psi. So if you write psi, what is psi here? So psi is nothing but is root over 3 by 3 phi 1 with 2 by 3 phi 2 and root over of 2 by 3 phi 3. Okay, so if you now take the inner product of phi 1 with psi, then it will nothing but phi 1 plus 2 by 3 phi 1 phi 2 and root over 2 by 3 phi 1 phi 3. So these are all 0, you know, because these are orthonormal gates. So only the term non-zero is phi 1 with phi 1. So this is root over 3 by 3 or 1 by root 3. So probability of getting the state phi 1 will be the inner product of phi 1 with psi square, which is nothing but 1 by root 3 square, which is 1 by 3. So this is the probability of getting the state phi 1. Now similarly, if you want to find out what is the probability of getting the state phi 2, then for that what you have to do, we simply have to take the inner product of phi 2 with psi square. So if you look at this uh, formula, this state representation, then only the term with phi 2 will be non-zero. So this will give 2 by 3 phi 2 phi 2 because other terms are non-zero. Sorry, 0. So this is square. So this will become 4 by 9. So now the probability of getting the state phi 3, this is nothing but phi 3 inner product with psi square. So this will become root over of 2 by 3 phi 3 so this will become 2 by 9. So up to now everything is clear to all, I think. If anyone has any doubt, then you can ask me. Okay. So the next part is it is asking about verify that the total probability is equal to 1. So you know that in any kind of system, the total probability will be 1. So if psi is represented as a complete expression of phi 1, phi 2, phi 3, and phi 4, then the probability of getting all this state, the summation will be 1. So let us check whether it is 1 or not. So probability of getting the state phi 1 is 1 by 3. Probability of phi 2 is 4 by 9. And probability of getting the state phi 3 is 2 by 9. So this is nothing but, so this is 1. So that means total probability is 1. It is always 1 total probability. Okay. So let us check the B part. So let me read out the question for you. So for the B part, it is asking about consider now a ensemble of 810 identical system, each one of them in the state psi. So now instead of a single system, we have an ensemble. Ensemble means identical copies of a system. Like if you have two pens, three pens, four pens, so it's in quantum mechanics what we told is it is an ensemble. So to find out, so here it is asking about consider now an ensemble of 810 identical system and each one of them is in a state psi. So all of them are in the same state psi. So if measurements are done all of them, then how many system will be found in each of this state phi 1, phi 2 and phi 3. So it is asking about among this ensemble 810. So let me write that down. So you have 810 ensemble. Now what is asking is among this 810 ensemble, how many ensemble will be in state phi 1, how many of them will be in state phi 2, and how many of them will be in the state phi 3. So for that, what you have to do, you have already calculated the probability of getting phi 1, probability of getting phi 2, and probability of getting phi 3. So to find out what is the number of state in phi 1, what you have to do is we have to just multiply the probability with the number. So you know that probability of getting the state phi 1 is, I think, 1 by 3. It is 1 by 3. So if we have 810 ensemble, so the number of state in phi 1 will be probability times ensemble 810. So 1 by 3 into 810, which is nothing but 270. So now if you have to calculate how many states are in phi 2 state. So for phi 2, it is the probability is 4 by 9. That means number of states in phi 2 will be P of phi 2 multiplied by 810, which is 4 by 9 into 810, and it is 360. And the last one is probability number of state in number of system in phi 3 state. Uh, so for that, the probability of getting the state is 2 by 9. That means number of states in phi 3 will be P of phi 3 into 810. This is equal to 2 by 9 into 810. This is 180. So these are the final result. Among this 810 ensemble, you will get 270 of them will be in state phi 1. So 360 of them will be in state phi 2. and 180 of them will be in state phi 3. Now measure if you want to measure the if you act an operator A on this state, so what will you get? You will get the eigenvalue A1, which is corresponding to phi 1 state. This is not a part of the question, but I am telling what will you get the results. Now this 360 of them in phi 2 state. That means if you act an operator, then the result will be the eigenvalue of phi 2. Similarly, for this, the eigenvalue of phi 3. So this is the first question. I think this one is clear to all of you. If you have any doubt, then ask me now. Otherwise, I will move to the next question. Okay. So let us see the second question. Read out the question once. Okay. So in the second question, it is telling consider a system whose state is given in terms of a complete or an orthonormal set of five vectors phi 1, phi 2, phi 3, phi 4, and phi 5 as follows. This is given to you. The state of the system is given. So, and it is also given phi n are the eigenstates of this system, Hamiltonian, and the action of an Hamiltonian is given in this form. So let me write what is given to us. So it is given psi equal to, the state is given 1 by root over 19 phi 1 plus 2 by root over 19 phi 2, 2 by 19 phi 3, and phi 4, and 5 by 19 phi 5. So this is given to you, and it is given phi n are the eigenstates of Hamiltonian operator H, and the action of the operator H on phi n is given by the eigenvalue and the eigenvector. So in this case, this is the eigenvalue of H operator. This is the eigenstate of H. So these are given with n is 1, 2, 3, 4, 5, and epsilon naught is a dimension of energy. Now, in the A part, let us see the A part. So A part is if the energy is measured on a large number of identical systems that are all initially in the same state. So what is it telling is we are measuring the energy of the system and on a large number of identical system, and all these system, let's say these are some kind of systems. So all this system is the same state psi. They all have psi state. Now, in this system, we are measuring the what will be the energy of the system. So now it is telling they are all in the same state psi. So it is asking what values would one obtain and with what probability. So now if in this all this system, if you measure the energy, then it is asking what will you get, and means what is the result you will get, and what is the probability. What is the probability? So it is asking about the result of a energy measurement and its probability. Okay. So let us see first whether in the postulate, what we see that the result of any kind of measurement is, let me read the right for you. So the result will be one of the eigenvalue of the system, eigenvalue of the operator which is acting on the system. Eigenvalue of the operator acting in the system. So now we are measuring the energy. That means the operator is Hamiltonian here, H operator. So the result will be the eigenvalues of Hamiltonian operator. Right? This is for the result. So let us see first what kind of result we will get. So let's see what is psi. So psi is, sorry, the eigenvalue equation is already given to you. This is H phi n equal to n epsilon naught phi n. In this equation, this is the eigenvalue. So this is what we have to report. Is what this is what is the result you will get. So the result will be eigenvalues which are n epsilon naught. So what will you get? N is 1, 2, 3, 4, 5. So you will get epsilon naught, 2 epsilon naught, 3 epsilon naught, 4 epsilon and 5 epsilon naught. So these are the result. These are the results of the measurement. Results that we will get if you act the Hamiltonian on the system. So these are the results. Now let us see the probability. So probability, if you see the postulate, then probability is given by probability of getting a state phi n is given by inner product of phi n with psi square divided by psi. Right? So first we have to check whether this psi is 1 or not. So psi is given to you. This is 1 by root of 19 phi 1, 2 by root of 19 phi 2. This checking of this psi n with psi n is easy. Now I think everyone can check whether these are normalized or not. So now let's check psi with psi. So it is nothing but 1 by 19 plus, sorry, it is 4 by 19, 2 by 19, 3 by 19 plus 5 by 19. So this is nothing equal to 15 by 19. So that means this psi is not normalized here. Okay. So you have to put this non-zero number in the final probability. Now let us see what is the probability. So we have energy eigenvalues. Epsilon naught, 2 epsilon naught, 3 epsilon naught, 4 and 5. So probability of getting this epsilon naught is same as probability of getting the eigenkette corresponding to this epsilon naught. So you know that eigenkette corresponding to this epsilon is phi 1, and for this is phi 2, this is phi 3, phi 4 and phi 5. So probability of getting energy value epsilon naught is same as probability of getting the state phi 1 after the measurement. So this is all you know, that this is inner product of psi 1 with psi divided by psi psi. Right? So this one you have calculated. Now let us see the numerator part. So if you see the expression for the state, you see the coefficient that is adjacent to the phi 1 is 1 by root over of 19. So only the inner product of phi 1 psi 1, if you take that, then you will get this non-zero number. Okay, so that means this is 1 by root over of 19. The upper part is 1 by root over 19 square. And this you have calculated now. This is nothing but 15 by 19. So this I think you will get 1 by 15. Okay. So this is the probability of getting epsilon naught after the measurement. So let's say probability of getting 2 epsilon naught, which is nothing but probability of getting state phi 2 after the measurement. So this is phi 2 psi square divided by psi psi. So phi 2 if you check, so if you take the inner product of phi 2 with psi, the only non-zero term is here, this part. All other terms will be 0. So it will be 2 by root over 19. I'm skipping the whole method of calculating this phi 2 with psi. I think everyone knows. If you don't know, then you can ask me. I can explain you. Otherwise, I can proceed. So this is nothing but 4 by 15. This is for the energy state E2, which is 2 epsilon naught. So for the 3 epsilon naught, let's quickly write down what is the probability. Phi 3 with psi square and psi psi. So phi 3 inner product with psi, the only non-zero term we will get is this one. Root over of 2 by 19. So root over of 2 by 19 square. This will be 2 by 15. Let's see if probability of getting 4 epsilon naught, which is nothing but probability of getting the state phi 4, which is the eigenstate of 4 epsilon naught. Phi 4 psi square divided by psi psi. So this is, if you check, this will be the only non-zero term. Other terms are 0. So it will be root over of 3 by 19 square. So this is 3 by 15. And the last one is probability of getting 5 epsilon naught, which is P5 5. And this is given by inner product of 5 5 with psi square divided by psi psi. So that means This is the last term, which is root over of 5 by 19. In square 15 by 19. So this is given by 5 by 15. So these are the probability you will get for each of this result. So what we see that we have a state psi and we act Hamiltonian on it. So after acting Hamiltonian on the state, what we will get? We will get the results as eigenvalues of H, and the probability is given by these forms. These are the probability of finding out a results. Is this clear to you? This question? I think it is clear to you. So let's see the B part. So B part is asking about find the average energy of the system. So let us see how can you calculate what is the average energy of the system. Average energy. So average energy of the system is given by the expectation value of the operator that is corresponding to energy. So the operator here is the Hamiltonian operator. So this is written as, if you are given a state psi, then this is nothing but psi divided by psi. This is the expression for the expectation value, which will give the average energy of the system. Now, there are many ways of calculating this expectation value. So let us see one of the way in which we can calculate the eigenvalue. So you know that H1 acts on this operator, this state psi, then it will give the eigenvalue phi n of and Cn, which is summation of, let's say, 1 to where 5 is there. So this when H operator, when it acts on a state psi, it will give eigenvalue with some eigenstate, which have eigenvalue n, and the probability is given by Cn. Okay. Now, uh, no, it is, I think it is incorrect. This is the expression for psi. This is Cn phi n. This is the expression for psi. So now when you act Hamiltonian on this state H, then what will happen? Cn is a constant. So Hamiltonian will directly act on phi n. This is this one you know. This one is nothing but the eigenvalue an with eigenstate phi n. Right? So from this one, you can easily calculate what is the bra vector. This is nothing but n equal to 1 to 5 Cn star bra phi n. Now, if you take the inner product of these two states, psi h psi, then what you will get is summation of n equal to 1. Let's say it is n dash Cn summation of n dash 1 to 5 n 1 to 5 Cn star Cn eigenvalue n with phi n dash with phi n. This is clear to you, right? This expression. So this one is nothing but the orthonormality condition. So this will give Kronecker delta. So that means it is only non-zero when n equal to n prime. So that means one of the summation term will vanish because n equal to n prime. Let's pick n. So this means Cn star, Cn eigenvalue n, right? So this is n equal to 1 to 5 Cn square eigenvalue n. So now if you take h with the expectation value, then this is nothing but dividing this summation term with inner product of psi psi. So this will give summation of Pn with eigenvalue n. Pn is nothing but the probability of getting a state pi n. So Pn here is Cn square divided by psi psi. This is according to the postulate, which expression is given by this. So that means you see that the expectation value can also be written as summation of probability of the eigenvalue n multiplied by the eigenvalue. Now you already know the probability and its eigenvalue. These are already know. These are the probability and this is the eigenvalue. So you have to just put the values in the final expression. So let's see P1. This is eigenvalue E1, P2 with eigenvalue E2, E3, E3 plus E4, E4, P5, E5. So E1, E2, E3 are nothing but the eigenvalues. E1 is epsilon naught, E2 is 2 epsilon naught, E3 is 3 epsilon naught, E4 is 4 epsilon naught, E5 is 5 epsilon naught, and this P1, P2, P3 are the probability of getting epsilon naught. P1 is probability of getting epsilon naught. P2 is probability of getting 2 epsilon, and similarly. So now what you have to do is you have to just put this probability and its eigenvalue in the final expression and get the result. So the final result will be this is 1 by 15 epsilon naught, 4 by 15 2 epsilon naught, 2 by 15 3 epsilon naught plus 3 by 15 4 epsilon naught plus 5 by 15 5 epsilon. So if you add these terms, then you will get the final as this. This is the final this is the average energy that you will get after the measurement. This is 52. So this is the question 2. Is this clear to all of you? If in any of this solving process, if you have doubt, then ask me. Otherwise, if you don't have any doubt, then let's see the third question. So So the third question is, it is telling, consider the problem where the Hamiltonian of the system is given by a matrix. So you know that any kind of the Dirac bracket notation can be written in terms of a wave mechanics term or a matrix form. So in matrix form, we represent operator by matrices. We represent the kth vector by the column matrix and the row vector by the bra vector by row matrix. So this is Hamiltonian is given, which is given by this. Now it is telling a particle is in the state represented by psi, and written in the basis is this. So what is given? Psi is given. Psi is given as 1 by root over of 3 I minus I and I. This is given. The initial state is given to you. Now it is telling, suppose energy of this system was measured. Now we measured the energy of the system, and also it is telling that we got a value of E equal to 1. So this is the value we got after the measurement. So what we do, we operate Hamiltonian operator on this, and we got a value which is nothing but the eigenvalue of H, and we got the value E equal to 1. Okay. Now this is given. Then subsequently we perform a measurement of a variable A. So after the energy measurement, we take another operator which is A, and which is denoted by this matrix A. This is the second measurement. So now it is telling, find the in the A part it is asking, find the possible results of A. So according to the postulates, the possible results of A, what will be the possible results of A? The possible results of A will be one of the eigenvalue of A. So now instead of a bracket notation, matrix notation is given. So you can easily find out what is the eigenvalue of this operator A. So in the first part, it is asking possible results of A, which is nothing but the eigenvalues of operator A. So we have to find out what is the eigenvalues. So eigenvalues is, how can you find out the eigenvalue of a matrix? So you solve this equation, determinant of A minus lambda I equal to 0. So the usual notation I think everyone knows. So lambda is the eigenvalue of A and I is the identity matrix. So let us see. So that means determinant of A minus lambda I. So what we will get is 5 minus lambda 0 0 0 2 minus lambda I 0 minus I 2 minus lambda equal to 0. And the determinant of this equation is 5 minus lambda multiplied by 2 minus lambda square plus I square equal to 0. So this means 5 minus lambda I square is minus 1. So you will get 5 minus lambda. This is 2 minus lambda minus 1 and 2 minus lambda plus 1. I have used the equation, use the formula a square minus b square equal to a minus b and a plus b. Here a is nothing but 2 minus lambda and b is 1. This is the equation I took. So this is equal to 0. So this is 5 minus lambda, 1 minus lambda, 3 minus lambda equal to 0. That means lambda is 5, 1 or 3. So these are the eigenvalues of operator A. Of operator A. So that means in the A part, the possible results that you will get is this one 5, 1 and 3. These are the possible results. Possible results of A. Now it is asking in the second part. Second part is important. So understand it clearly. So now in the second part, it is asking what are the probabilities of obtaining each of this result found in part A. So in part A, you got 5, 1 and 3. So now it is asking what is the probability of getting 5, what is the probability of getting 1 and what is the probability of getting 3. So this one is a bit, you have to careful to find out the probability because in this part already one measurement is done, energy measurement is done. Now you are measuring the operator A. So what, so how can you find out the probability? Let us see. So what you have to do is to find out the probability, you have to write the final state in terms of the eigenstate of the operator A. Let's say A is acting, so you have to find out the probability. You have to first write the final state in terms of this eigenstate. So what is the final state now? Now you have seen that already energy measurement is done. So psi was there and we act Hamiltonian on it. So what we got? We got a value of E equal to 1. So that means now we are acting. We don't know about what is the state of the system here, but this state will be the eigenvalue of equal to 1. Sorry, eigenstate of equal to 1. Now in this state, we are acting the operator A. Okay, and we are getting the value 5, 3 and 4. Now it is asking what is the probability of getting this 5, 4, 3. So now for that, what you have to do, we have to write this state, the state here in terms of the eigenstate of 5, 3 and 4. Okay, so let us first find out what is the state here. Okay. What is the state here? So this is nothing but we got a value of equal to 1. That means the state will be the eigen state of H corresponding to equal to 1. The state will be the eigenstate of H corresponding to equal to 1. So how can you find out the eigenstate now? So for the eigenstate, we know the eigenvalue, so we just have to solve the eigenequation, which is nothing but HU equal to EU. This is the eigenequation, eigenvalue equation, and here U is the eigenstate, which have eigenvalue equal to 1. So given E equal to 1, so this is nothing but U. So let us put the expression for H. H is nothing but 2, 1, 0, 1, 2, 0, and 0, 0, 3. So this is 2, 1, 0, 1, 2, 0, 0, 0, 3, and this is A, B, and C. Let's say U is written in terms of A, B, C. We don't know the components, so we are assuming it is some coefficient A, B, C. So you just have to solve this equation, matrix equation. So what will you get? The first row will give 2A plus B equal to A. Second row A plus 2B equal to B. Third row 3C equal to C. So from the third row you see 3C equal to C. That means this is not possible. 3C equal to C cannot be possible. So that means C is itself 0. And from this two equation you will get one other expression, which is B equal to minus A. So that means now the U is given by A, B, C, which is nothing but A minus A and 0. So in quantum mechanics, we always use the orthonormal case. So let's normalize it. So you have to normalize it by dividing this ket vector with its norm. Okay, so if you do it now, you will get 1 by root 2, 1 minus 1, 0. So that means the state here, is nothing but U, which is given by 1 by root 2, 1 minus 1, 0. So now we know the intermediate state that is here. So now what we have to do is to, so let me write it again. We have psi t, we have psi, then we act h upon it, then we got u, which is given by 1 by root 2, 1 minus 1, 0. Then we act a on it, and we get the eigen gates, let's say u1, u2, u3 of A with eigenvalue 5, 1, and 3. So so it was asking what is the probability of getting 5, 1, 3. So what we have to do is we have to express this u in terms of this, in terms of the eigen vectors of A. Okay, that means we have to express it in terms of u1, u2, and u3. So you already know the eigenvalues. So to find out the eigenstate, you have to just solve the eigenvalue equation, which is given by A ui equal to an, not n, ai and ui. So using this equation, you can find out what is the u1, u2, and u3. So to get u1, you have to solve A U1 equal to A1 is, let's say, 5. We are taking A1 is 5, A2 is 1, A3 is 3. This is 5 A1. So similar to the previous case, we have to just put the matrix to A, which is given by this one, 5 0 0 0 2 I and 0 minus I2. So we have to put it here, 5 0 0 0 2 I and 0 minus I2. And for U1, you just take some coefficient, unknown coefficient ABC, and solve this matrix equation. So this for the I'm solving for the first one. For the next U1, U2 and U3, I think you can solve. Let me just show for the U1. So this is 5A equal to A. This is 2B plus IB equal to 5B. And the last one is minus IB plus 2C equal to 5C. This is 5A equal to A. That means A equal to 0. This is not possible, right? 5A equal to A is not possible. So that means A equal to 0. So for the second case, uh, this 2, I think you will get, let me see what is the eigenvalue you will get. So for the 5 case, you will get 100. Oh, sorry. Hmm. So this is 5A equal to 5A, I think. So it is not equal to 0 here. So equal 5A. Okay, if you solve this now, you will get U1 equal to, the normal is get U1 equal to 100. Just solve these equations, then you can easily get. Now for the other uh, eigengates, what you will get, U2 you will get, U2 is the eigenvector corresponding to lambda equal to 1. This one you will get 1 by root 2, 0, 1 I. And for lambda equal to 3, you will get U3 equal to 1 by root 2, 0, 1 I. I'm leaving this whole calculation to you because you just have to calculate, just have to solve this matrix equation and find out this one. So now we find out what is the eigenvectors of operator A1, A. Now you have to write U, this intermediate state U in terms of U1, U2, U3. Is equal to summation of Ci Ui I equal to 1 to 3. Now to find out the probability is given by this Ci square. So Ci square, which is nothing but the inner product of, it is not phi here. So it is Ui with U square, right? Oh, let me write it again. So U is now written as the linear combination of the eigenstates of A operator. These are the eigenstate of A operator. That means this is C1 U1 plus C2 U2 and C3 U3. U is normalized, right? Because we already calculated U is here. So we already took the normalized eigengate. So that means UU equal to 1. So probability of getting a eigengate U1 will be, according to the postulate, it will be given by uh, U1 U square divided by U U. And this is equal to 1. That means this is simply given by U1 by minor product U square, which is nothing but C1 square. This is the probability. So now you already have U1, you have U2, U, the matrix form. So U1, you have, that is the expression 100. This is U1, this is 100. That means the bra U1 will be 100, the row vector, and U is given 1 by root 2, 1 minus 1, 0. So that means U1 U equal to, this is 100, this is 1 by root 2, 1 minus 1, 0. So this one you will get, what you will get? This one you will get 1 by root 2, right? And the probability of getting U1 is the square of this inner product, which is 1 by 2. Similarly, this is the probability of getting U1. This is similar to probability of getting the eigenvalue corresponding to U1, which is nothing but 5. So this is probability of getting a 5 after you act a operator on it. So this is half. Similarly for U2, probability of getting U2, that means probability of getting eigenvalue 1. So this is given by U2U inner product square. So just put the matrix equation. U2 is 1 by root 2. This is U2. So this one you will get 1 by root 2, 0, 1, minus I. Here I, this I will become minus I when you take the bra. Minus I, and U is 1 by root 2, 1 minus 1, 0. This is square. So 1 by root 2, 1 by root 2 is half, multiplied by this matrix multiplication, you will get 1. So the final probability you will get is 1 by 4. So this is probability of getting eigenvalue 1. Similarly, probability of getting U3 or probability of getting eigenvalue 513, then it is given by U2U square. Sorry, U3 U square. So if you check this one, you will get the same value 1 by 4. Okay. So this is how you can calculate the probability and the results if you are given two operator. Like for one operator it is okay, but if you are given two operator, like in this case, the first operator is Hamiltonian operator and the second one is the unknown operator A. So for that, if they are asking about what is the probability of getting a result here, so you have to see what is the state before. Okay, let me write it properly. So if you are given in this situation, two operators are given. One Hamiltonian operator and another one is A operator. So if they are asking about the results here and the probabilities here, so first what we have to do is we have to find out what is the state here. What is the state? Let's say phi here. Then after getting the state phi, what we have to do is we have to represent it. We have to express it in terms of the eigengates of this operator A. So let's say A is eigenstate phi n. So we have to represent it as a summation of Cn phi n. So you have to take express in terms of eigenstate of the operator that is acting on the last. Then from that you can easily find out the probability. So while calculation, don't take this initial state as a initial state to find out the probability, because this will give wrong result, because already the state the system is getting perturbed. So if you are in quantum mechanics, if you act on any operator, then the state of the system changes. So according to that, you have to check whether the state is same or not before the measurement. If not, then you can take, if it is already a one operator is acting on it, then you have to find out what is the state of the system after the measurement. Then you have to express it in terms of the eigenstate of the operator asking. So this one is, I think, clear to you. So let's see one of the easiest question first, then I will take one. This one. Let's see. Let's solve this question first. Then we can move to another uh, problems where concepts are there. So this is a simple question. So it is asking about calculate the commutator between the x and y component of the orbital angular momentum. So it is asking about what is the value for the Lx and Ly. What is this value? So you know that the orbital angular momentum is given by r cross p. If you write it as in matrix form, you can write it as x cap, y cap, z cap. R is, let's say you have x component as x cap, y, z, x component of position, then the momentum, x component of momentum is px, y component of momentum is py, and z component of momentum is pz. So this is, then you have to just solve this matrix to find out what is the Lx, Ly and Lz. So for the x component, what we have L pz minus z py. This is x cap. For the y component, this one, what you have to do? You have to multiply this with this and minus this with this. This is minus 1 x cap pz minus z px, and the last one is, this is y cap, and the last one is z cap. For that you have to multiply x with py, y with px. So this is x px, x py minus y px, z cap. So this means this is nothing but Lx x cap plus Ly y cap plus Lz z cap. So this is Lx, this is Ly, and this is Lz. So let me write out Lx, Ly, Lz for you. So Lx is nothing but y pz minus z py. Ly is z px minus x pz. Similarly, Lz is x py minus y px. Okay. So now it is asking about the commutator of Lx and Ly. So for that, what you have to do, you have to just take the these two expression, Lx and Ly. So this is nothing but y pz minus z py and z px minus x pz. So now what you have to do, you have to just solve this commutator relation. Like if you are given a plus b and c plus d, then you can write it as ac plus ad plus bc plus bd. So use this in this equation. So the final what you will get is, let me show you the sir. So the final we will get is this is the you take y with this one, the first term with this one, then you take second term with this one, and third term with this one. So this is the whole term. Okay. So now for the individual case, what you have to do, you have to just open this bracket, like you just have to take, like, this is nothing but A, B, C, D commutator form. So what you have to do, open the bracket and solve it. Means group the similar terms. So if you group it, what you will found is this term y pz z px, and the second term is x z pz py. So this one you already know. This one is PZZ is nothing but minus IH cut and ZPZ is IH cut. So just put the commutator relation, then you will get the final form as this. This is the expression for LZ, so you will get IH cut LZ. So this is one of the easiest question that you can solve. So let me move to the, let me start. Fourth question. So fourth question is kind of similar to the third question, but it's a little bit different. So if you see the fourth question, up to now everything is clear, right? Every question is clear, right? If you have doubt, then ask me. Otherwise, I will proceed with the fourth question. So okay, so let's see the fourth question. So it is given an operator A corresponding to an observable alpha has two normalized eigenfunction phi 1 and phi 2. So one observable alpha is given. It can be any kind of observable like position, momentum, angular momentum. So this is one of the observable, and the operator corresponding to it is A, and it is given that the eigenfunction of this operator, normalized eigenfunctions are phi 1 and phi 2. And it is given the eigenvalue corresponding to this eigenvector phi 1 is a1 and phi 2 is a2. This is given. Now it is the second sentence. It is given an operator B corresponding to an observable beta. So Now we have another kind of observable which may be different than alpha. We have observable beta, which corresponding to an operator B. So according to postulate, we know that we can write the observable as an operator. So now it is given the eigenfunction of this operator is chi1 and chi2. And the eigenvalues of this chi1 is beta 1, b1 and chi2 is b2. And what is also given is the relation between this eigenfunction phi1, phi2 and chi1, chi2 of different operator. Mm, This is given phi1 equal to 2 chi1 plus 3 chi2 by root over of 13. Another one is phi2 equal to 3 chi1 minus 2 chi2 divided by root over of 13. So this is given. Now it is telling we measure the alpha. So first we measure the alpha, then we got a value of a1. So first what we measure? We measure alpha, then we got value a1. Now, now it is telling if beta is then measured and then alpha again, then what is the probability of getting a1 after such measurement? So what is the process is? The process is like this. So first measure alpha, then we got value a1. Then what we are doing? We are measuring beta. Then we are also so if we measure beta, then what we will get? We will get the eigenvalue of beta, which is b1, b2. After that, what it is saying that we again measure alpha. Then it is asking what is the probability that we will get a1 here. So initially we get a1 here. So what is the probability that we will get a1 also here after another measurement? So it is asking about what is the probability of a1 getting here after this sequential measurement. So let's see the process first. What was given to us? We measure alpha and we got a1. So this tells us that the state, the state here the state. So when we, let's say we have a state psi and we act alpha on it. So the state and we got a1 here. That means the state here will be one of the eigenstate of alpha, which have eigenvalue a1, right? And in this slide, you can see the eigenvector that is corresponding to the eigenvalue a1 is phi 1. So that means the state here is phi 1. The state here is phi 1. So this means that when we act alpha on psi, we got phi 1 state. This we calculated that we got a state phi 1 here. Now what we have done is we again act beta on it. So if we act beta on phi 1, what we will get is we will get the eigenvalues of the beta operator, which is b1, b2, and the state will be the eigen states of beta, which is nothing but chi1, chi2, right? So that means if you act beta on phi 1, then the state after the measurement will be either chi1 or it will be either chi2. Because we will get two types of eigenvalue, which is b1 or b2 with some probability. Okay, it is not like it is completely chi1 or it is completely chi2. It will be a linear combination of chi1, chi2. So it is like summation of bi chi I, where I equal to 1 to 2, right? So, now let us check what is the probability of getting chi1 and what is the probability of getting chi2. So for that, what we have to do? So probability of getting chi1 is nothing but, so first what you have to do is we have to express the state before chi1 in terms of the eigenvectors of chi1. Like the state before beta acts on it, like alpha act on the state psi, it gave phi 1. Then we are acting beta. Then we will get, so let me write it properly. So it is given alpha act on a state psi and it gave phi 1. Now we are acting beta. Then it will give a linear combination of the eigenstate of beta. So to find out the probability or find out the probability of getting chi1, probability of getting chi2, what you have to do is first express the state before the measurement. The state before measuring beta is nothing but phi 1. So express it in terms of chi1 and chi2, because before the measurement we had that state. So that state only give the probability. So and this is given in terms of chi1, chi2. Phi 1 is already given in the question. You don't have to calculate. This is given. This is nothing but 2 chi1 plus 3 chi2 by root over of 13. So phi 1 given is 2 chi1 plus 3 chi2. I am writing in terms of bracket notation so that the inner product will vanish whenever there is some orthonormality. So this is given. So that means and check whether phi 1 is normalized or not. Phi 1 is normalized because it was given these are orthonormal eigenfunction, or otherwise we will check also. So this will nothing, this will give 4 by 13. This will be 9 by 13. So this means this is already normalized. So that means the probability of getting chi1 is nothing but the inner product of chi1 with phi1 square, and probability of getting chi2 is chi2 and phi2 square. Not phi2, phi1, because phi1 was there. So this one, if you check for the first one, you are seeing that uh, only the 2 by root over 13 chi1, 3 by root over 13 chi2. So for this one, this term will give non-zero quantity, this ked vector. So we will get 2 by root over of 13 square, which is nothing but 4 by 13, right? 13 square. No, no, it is 4 by 13 only. This is 4 by 13. No, and for the second probability, only this chi2 will give the non-zero value. So the inner product will give the coefficient, which is 3 by root over 13. So this is 3 by root over 13 square, which is nothing but 9 by 13. So what you get now is probability of getting state psi. So now you got the state here, which is let's say chi here, which is 4 by 13 chi1 and 9 by 13 chi2. So this is the state here. Uh, here. Now what we are doing is we are again operating the operator alpha. So after beta we are again operating alpha. So let's see what will we get now. So up to now what did we get? Alpha psi, then we act alpha, we got phi 1, then we act beta, then we got linear combination of chi 1 chi 2 by chi 1, which is nothing but what did I get? 4 by 13 chi 1 and 9 by 13 chi 1 plus 9 by 13 chi 2. Now what we are doing, we are again acting the alpha. This is the final state. We are again acting the operator alpha. So now it is asking what is the probability that you will get A1 here, right? So probability of getting A1 here, if write it as PA1, it is same as probability of getting the eigengate, that is eigenvalue A1, which is nothing but phi 1. So this we have to calculate. So as I said, what we have to do is, again in the last step, we have to check what is the state here and express the state here in terms of the eigengates of the operator that is acting on it, that is alpha. So eigengate of alpha is phi 1, phi 2. That means we have to express the state here is nothing but chi 1 and chi 2. So we have to express chi 1 in terms of phi 1, phi 2 and chi2 in terms of phi 1, phi 2. For that, what we have to do is we have to just use the equation that is given to us. Like this equation is given to us, right? This is the equation that is given to us. Huh. So equation given to us is phi 1 equal to 2 chi 1 plus 3 chi 2 divided by root over of 13, and phi 2 is 3 chi 1 minus 2 chi 2 by root over of 13. So using this equation, we can express chi 1 chi 2 in terms of phi 1 phi 2, right? So phi 1 phi 2, chi 1 chi 2, what we can get? Chi 1 chi 2 we get is 2 phi 1 plus 3 phi 2 divided by root over of 13, and chi 2 we will get is 3 phi 1 minus 2 phi 2 divided by root over of 13. So this is the uh, expression we will get. So now we have chi 1 chi 2 in terms of the eigengates of, we know the we have chi and chi 2 in terms the operator alpha, right? So now to find out the probability, what you have to do is, so now we have chi 1 equal to 2 phi 1 plus 3 phi 2 divided by root over of 13, and chi 2 is nothing but 3 phi 1 minus 2 phi 2 divided by root over of 13. Now to find out the probability of getting A1, what you have to do is we have to take the inner product. Inner product of inner product of phi 1 with phi 1 square, and another inner product what you have to take is A2, which is phi 2, sorry, phi 1 with chi 2 square. So this you get if you see this equation, you will see that the inner product will give 2 by root over 13 square, which is nothing but 4 by 13. And for this, if you see this expression, then you will get phi 1 with chi 2. So you will get 3 by root over 13 square, which is nothing but 9 by 13. So now to calculate the total probability, what you have to do, let's say the whole series. We had state psi, then we had alpha, we got phi 1, then we act beta, then we either got either chi 1 or it may be chi 2, and the probability of chi 1 is we had calculated 9 by 13, 4 by 13 and 9 by 13 here. Chi 2 is 9 by 13. So this is 4 by 13 and this is 9 by 13. Probability of getting chi 1 here, probability of getting chi 2 here. Now, if we had state A1, chi 1, then probability of getting A1 is then given by 4 by 13 into 4 by 13, which is 16 by 169, right? Because already 4 by 13 was here and another 4 by 13 we got here. So you just multiplied the two factors. So now similar for this, if the state is in the state chi 2, then probability of getting A1 here is nothing but probability of getting chi 2 and probability of getting A1 when the state in chi 2. This is A1. So this is nothing but 9 by 13. And probability of getting A1 when the state in chi 2 is this. So 9 by 13. So this is 81 by 169. Similar for this is nothing but probability of getting chi 1 multiplied by probability of getting A1 when the state is in chi 1. Now the total probability will be the summation of all of this. So the total probability of getting a state, getting A1 is nothing but 16 by 169 plus 81 by 169, which is nothing but 97 by 169. Okay, I think all these questions are clear to you. So let's stop here. Uh, so thank you everyone for joining the section. So let's stop this section now and we will solve some more question in the next Saturday. So thank you all. Bye.